Hello and welcome. Refrigeration and heat pump cycles, which are mostly vapor compression and gas refrigeration cycles, are covered in chapter 10. We'll go over a few animations, but before that, um, notice that we have already gone over vapor power cycle. So that will be a good place to start. So you should go over vapor power cycle before going over refrigeration cycles, because refrigeration cycle is basically vapor power cycles in reverse. For instance, for gas refrigeration, you should go over the gas turbines cycle, like Brayton cycle. Okay, so here is a schematic or an animation showing an ideal vapor compression cycle. As you can, it's almost like a Rankine cycle on reverse, except instead of a turbine, we have an expansion valve here, where enthalpy remains constant. There are other modification of this cycle. For instance, this is a modification. It's called cascade refrigeration to achieve a very low temperature, and this is an example of a gas-powered cycle used in aircraft. It's a reversed Brayton cycle, which can be used to cool down a gas, or just opposite to a gas turbine engine. Okay, so let's go and quickly show you where the apps are and how the problems are solved. Okay, for refrigeration cycle, if you're just interested in overall analysis, then of course you can go and do a closed cycle analysis, which will give you overall COP, etc. But for details, we have to go over open systems, specific branch, and this is where the vapor compression and gas refrigeration cycles are. And of course, if you want to do vapor compression cycle, as in a household refrigeration system, go to the PC model, and there are a bunch of examples here. And we'll pick up the simplest example, the test code for that, and we'll copy that for the sake of time. And as you can see, the test step looks just like the vapor compression cycle. Here, just like the vapor power cycle, except the state panel is identical, and any other flow state looks like that. Graphic panels is just the same. Device panel, you'll notice that exactly the same as any open steady device analysis panel. And the cycle panel is where it differs slightly, because when it puts together all the devices, instead of efficiency, it calculates the COP, for instance. So we'll go and reproduce the solution I'm putting in the test code. Notice that the way the test code has been written, we have isolated as user code the condenser pressure and the evaporator pressure. So in other words, these two pressure can be used for a parametric study. Any variable that you are interested to be a parametric study, it's a good idea to define that in the I/O panel, and then use that in the state panel. So let's first load this code. It automatically does a super calculate, and as you can see, state 1 is shown as this is the exit to the evaporator, state 1. So it will be clear if you go to the graphics panel. State 1 is here. So 4 to 1 is the evaporator, 1 to 2 is the compressor, and 2 to 3 is the condenser, and 3 to 4 is the expansion valve. If we do a constant pressure line through state 1, the pressure remains constant along the evaporator, and if you do a constant pressure line over state 2, you can see, by the way, this guy's toggle, so if you click again, it will go away, it will come back if you click again. Okay, so in the device panel, as you can understand, device 1 is our compressor, therefore the work is found where the heat transfer is 0. Device 2 is the condenser, so heat is rejected, negative heat, no external work transfer. Device 3 is, of course, the expansion valve. There should be no heat transfer, no work transfer. And device 4 is the evaporator. So this is where, this is how much heat you can find the tonnage of the refrigeration system. It's a 1.5 ton refrigeration system. If you go to the cycle panel, everything is put together here, and you can find the COP has been calculated. The net power is calculated, how much compressor power it absorbs. Well, I'll stop here, and you can obviously do a parametric study very easily by going to the I/O panel and say changing any parameter, like how will the evaporator pressure affect, for instance, the COP. It's just a matter of changing the number and doing a super calculate. Of course, chapter 10, as in animation, chapter 10 in problem section, we'll have plenty of problems on refrigeration and heat pump, and the gas refrigeration problems are also included here. And for the sake of time, I'm not solving any problem here, but you can understand that a gas refrigeration is just like the Brayton cycle problem that we have covered in chapter 8, except this is in reverse.